Welcome back. In this video, we can start discussion about the control logic design of a computer system. So these are the basic functional units of a computer, like input output unit, memory unit, arithmetic and logic unit, and finally the control unit. In our previous videos, we had discussed about the organization of this IO unit, memory unit, arithmetic and logic unit. Now we can consider this control unit design. First of all, we can consider the functionalities of a control unit. It maintains order and direct the operation of our entire computer system. So it directs the activities performed by our computer system. It controls all other devices like memory, input, output devices connected to our central processing unit. Activities of all other functional units are controlled by our control unit. And another functionality is it decodes the instruction available in our instruction register. That means after fetching an instruction from the memory, that instruction is placed into our instruction register. That activity is controlled by our control unit. After that, the instruction available in the instruction register is provided as an input to the control unit. The control unit decode the instruction and interpret the meaning of the instruction present in the instruction register. Based on that information available from the decoder instruction, it generates certain control signals in order to perform certain set of activities. That means the control unit decode the instruction available in the instruction register and identify what operation want to perform next. So based on that, it generate corresponding control signals. Okay, it gives order to ALU what operation want to perform. That means after decoding the instruction available in the instruction register, it identifies what operation want to perform next. So it generates sometimes control signals for the ALU. That control signal acts as an order to the ALU in order to start the execution of certain operation. And also this control signals controls data flow between CPU with peripheral devices like input output devices and memory. Control the data flow through the buses. And also it provides status information, control information and timing signals to the peripheral devices. That means it provides status information. The status information means the condition code flag values. That values are used by the ALU in order to execute various instructions. Or the status information or the condition code flag values are used by ALU in order to perform certain operation. And also generate various read and write control signals and interrupt relate control signals, etc. And also generate timing signals. This timing signals actually decide the clock cycle period in order to finish certain set of micro operations. Okay, so these are the basic functionalities of our control unit. So this particular diagram shows the interaction between control logic and the processing unit. Okay, so control logic of our system with respect to various external input provided to the control logic, it generates certain control signals. These control signals act as an order to the processor in order to start the execution of various operations by using the input provided and generate the output value. And also it parallelly generates certain status information. That status condition are passed back to the control logic, so that control logic can update the condition code flag values based on the updated status information provided by the data processor. Okay, so this particular diagram shows the interaction between control logic and processor. Next is about the input and output of our control unit. Control unit is provided with three different inputs. Master clock signal, input from the instruction register, content of the condition code flags. Master clock signals actually provided to the control unit externally. Using this clock information, this control unit can identify the start and end of various control signals. Start and end of various clock cycle. In a single clock cycle, the system can execute a single micro instruction or a sequence of parallel micro instructions. So, with the help of external master clock signal, the system or the control unit can identify the start and end of various clock cycles. Within a single clock cycle, the system can complete a single micro instruction or a sequence of parallel micro instruction. And the input from the instruction registers are used for instruction from the instruction register are provided to the control unit, and the control unit can decode it and interpret the meaning of the instruction that is going to execute, so that after decoding it generate corresponding control signal. And also the condition code flag values. Condition code flag means zero flag, sign flag, overflow flag and carry flag. The current value of these condition code flag values are taken as an input to the control unit. Based on the current values of these condition code flag, the control unit can trigger certain control signals in order to activate or in order to control the operation of our processor. So these three are taken as an input to our control unit. And always the control unit output are the control signals. These control signals are used for controlling the activities of our processor. Okay, and also these control units are provided to the external control bus in order to control the data transfer through the external bus. So the output of the control unit are control signals used for controlling activities of or the execution of micro operations by the CPU or the ALU, and also for controlling the data transfer to the buses. Okay, now here we have 4 different methods for the design of our control logic. Control logic can be organized with the help of these 4 different methods. What are these 4 different methods? One flip-flopper state method, sequence register and decoder method, PLA based control method, microprogrammed control method. We can consider each of these separately. First of all, about the one flip-flopper state method. So this is the diagram representation. Here we have 4 different flip-flops. Each of these flip-flop represent different condition states. And these condition states are controlled by a decision logic. And decision logic can decide different state with respect to the external input condition provided to this logic. Next is about the operation of the system. Only one flip-flop is set at any particular time. All others are cleared. These 4 different flip-flops here indicate 4 different conditional states. Only one flip-flop is set at any particular time. That means only one condition state become active at a particular time and all others are in cleared state. For that, a single control bit is made to propagate from one flip-flop to other under the control of this decision logic. A single control bit is made to propagate from one flip-flop to other under the control of a decision logic. Okay, so that particular each flip-flop represents a state and is activated only when the control bit is transferred to it. Suppose this decision logic want to activate state T1 now. So that decision logic want to enable this flip-flop, this particular flip-flop. That means with respect to the current external input condition, this decision logic want to activate state T1 now. So the decision logic try to activate this flip-flop. For activating this particular flip-flop, what we want to do? We want to get the control bit here now. Okay, we want to get the control bit here now. Actually, that control bit is propagating through this for different flip-flop. And if this decision logic want to activate this particular state, we want to activate this particular flip-flop now. For activating this, the decision logic make that control bit available here now. Okay, so this is the working of this particular one flip-flop or state method. What state want to activate? In that particular flip-flop, the control bit become available. Okay, if we want or if this decision logic want to activate state T2 now, then the decision logic make that control bit available here in this particular flip-flop. And all these decisions are taken by this decision logic with respect to the external input condition. Okay, and also this decision logic can decide or select some other condition state other than this T0, T1, T2, T3. That is why an external extra control output line here. This can select some other condition state, some time instant. It can select some other condition state other than this 4 in some time instant, so that here it provided an extra condition line. Okay. So what is the advantage of this one flip-flopper state method? The circuit is very simple, and so designing such a system is very simple, effortless. But the disadvantage is here in this particular representation we have only 4 state. 4 flip-flops are available, so 4 different state can represent it. If we want to represent more number of state, in that case we need to attach more number of flip-flops. So if we want to represent more state, then system become costly. So second is about the sequence register and decoder method. So in this we have a decision logic as mentioned in our previous case, and a sequence register with n number of bit. That means sequence register with capacity n bits, and a decoder unit. Okay. So in this method, it uses a register to sequence the control state. So with the help of this sequence register, we can control various states. The register is decoded to provide one output for each state. So the current value available in the sequence register decide what state want to active now. So this decoder output decide n different states. So the current value of this sequence register decide what state become active now among the n different state. Suppose the sequence register with n bit capacity, then the decoder can output 2 raised to n different state, or the decoder output represent 2 raised to n different states. So based on the current value of this sequence register, the decoder can activate only one among the 2 raised to n different states. Okay, so based on the external input condition, current external input condition, and the present state of the system, the present state is available from the output line of this decoder. So based on these two information, our decision logic can decide which state want to active now. So that particular information is loaded here into our sequence register. So after decoding the information of our sequence register, decoder can activate only one of its output state. Okay, so suppose our sequence register with capacity 4 bits. In that case, its system can represent total 2 raised to n, that is 2 raised to 4, equal to 16 different states. That means decoder output is attached with 16 different states. And this decision logic based on the current external input condition and current present state of our system, this decision logic can decide what state want to active next. So that particular information is loaded into this 4-bit sequence register. So after decoding that information available now in the sequence register, decoder can activate one of its output line among the total 16 different output. Okay, and one more, if this decision logic want to activate some other conditional statement other than the 16 different state possible with this decoder, if this decision logic want to activate some other condition statement, then it can separately activate using this control output line. Without using this decoder and sequence register combination or circuitry, the decision logic can decide or activate or generate some other control signals using this external output line. Okay. Next is about the PLA based control logic design. That means this PLA control logic is similar to the sequence register and decoder method. Okay, so instead of our decoder and decision logic, here we have a PLA circuitry only. By using the PLA for combinational circuit, it is possible to reduce the number of ICs and the number of interconnection wires here. So using this PLA circuit here, we can reduce number of circuitry needed for the implementation of our previous sequence register and decoder based method. We can reduce the circuitry requirement here. Okay, so the PLA output determines the condition state. That condition state can activate different micro operations. Okay, so the PLA can decide one of the condition statement. That condition statement or the condition state activate different micro operations of the system. And the PLA can activate a particular condition state with respect to the current state of the system and using the current external input condition. So based on the current external input condition and the system present state, this is system's present state information is available from this sequence register. Okay, so the present state information from the sequence register and the external input conditions are used by the PLA in order to decide what condition state become active next. So after activating a particular condition state, it can start the execution of different micro operation by the system. So this is about the PLA based control logic. Next is about the microprogram based control logic design. And this method, control variables at any given time can be represented by a sequence of zeros and ones. So different control statements that can be called as control variable. Different control statement or the state can be represented as a string of zeros and ones. So that particular control state is called a control word. A control word means sequence of zeros and ones. That control word actually pointing to a particular control state. Okay, the control word can be programmed to initiate the various components in the system. That means this control word is actually a string of zeros and ones that indicate a particular control state. That control state can activate different micro operations in our system in an organized manner. The control unit whose control variables are stored in a memory system is called microprogrammed control unit. That means in the design of a control unit, All such control words are stored in a particular memory system. Then such control unit design is known as microprogram based control unit. In a microprogram based control unit, the entire activities of the systems are controlled with the help of various control words. These control words are stored inside a common memory. Okay, such a design of control unit is known as microprogram based control unit. Each control word of the memory is called a control instruction. Okay, the control word is actually sequence of zeros and ones, right? That sequence of zeros and ones actually indicate a particular control state. That control state can trigger various micro operations by the system. All such control words are collected together inside a common memory. Such a system or such a control unit design is known as microprogram based control unit design. Okay, inside such a memory, each and every control word indicate different instructions, which is known as control instruction. Okay, in order to activate certain set of operation by a particular functional unit, we need n number of such control instruction sequence. So, a sequence of such control instruction together form a microprogram. So, in a microprogram based control unit design, sequence of control instructions form a microprogram. So, with the help of a microprogram, we can activate a sequence of operation by a particular functional unit of our control system. We can activate a sequence of operation by a functional unit of our computer system. Okay. The use of microprogram involves placing all the control variables in words of the ROM type memory. Usually, ROM type memory is used for storing control words of a microprogram based control logic design. ROM type memories are used here because these control words are predefined and we can permanently store them inside a memory. And during the time of system execution, we can read each and every control words as and when required. So that the best option for such a storage space is ROM type memory. Okay, so this is such a representation for microprogram based control logic design. Here we have a next address generator unit, control address register and a ROM type memory in which all the control words are stored as a separate memory word. So based on the next address information provided by this control memory to the next address generator, the next address generator use the current external input condition also as an input. So using these inputs, it generate a next address information. That next address information actually indicate a particular memory word of this ROM. Okay, so that generated address is loaded into this control address register. So after decoding this address information currently available in this control address register, we can fetch a particular memory word of this ROM. That particular memory word actually indicate a particular control word that can indicate or generate certain control signals. That control signal can initiate the execution of a certain set of micro operations. So this is about the design of microprogram based control logic of our computer system. Okay, the next address generator can generate address of the next control state that is loaded to this control address register. After decoding the address information available here, we can fetch a particular control word from this ROM memory, control memory. Okay, that particular control word can generate the control signal for initiating the execution of a set of micro operations. Okay. So all these four are the basic four methods of designing a control logic of a computer system.